OCR A, A-level physics. This is my third video on gravity and astrophysics, and this video is about stellar evolution. Okay, now pretty pictures coming up on the next slide. Just basically make sure you know this pretty basic stuff. What is a planet? Well, a large body that orbits a star. There's a few other conditions. It has to have enough gravity to pull itself into a sphere and to clear its orbit of smaller objects. Pluto isn't a planet because there's actually about half a dozen things which are actually bigger than Pluto, other dwarf planets. And Pluto is in what we call the Kuiper belt, so it hasn't cleared its orbit. There's loads of other junky bits out there as well. A planetary satellite, an object that orbits a planet, for example, the moon. A comet, a large ball of dust and ice that orbits a star with a very large eccentric orbit. In other words, it's not a circle, it's an ellipse, a very eccentric ellipse. When they're close to the sun, then the solar wind creates this very distinctive tail. And also bits falling off as well creates a tail. Comets have two tails. Solar system, a star and all the stuff that is in orbit around the star, which is planets and dwarf planets and asteroids and comets, etc. A galaxy, a huge collection of gas and dust and billions of stars held together by gravity. The Milky Way has at least 200 billion stars in the Milky Way. Lots of stars in the Milky Way. And then the universe is like universal. It's all of space and its contents, including at least 200 billion galaxies. So at least 200 billion galaxies, and those galaxies have at least 200 billion stars, or at least 100 billion. So the universe is big. And that's the known universe. That's what we know. Here's some pretty pictures. There's Jupiter. It's a planet. There's the moon. It's a moon. There's Halley's Comet. That top right, Halley's Comet. Bottom left, you've got a solar system. So you've got your sun. You've got these 4 planets, you've got the asteroid belt, you've got these gas giant planets there, then you've got the what we call the Kuiper belt, and then see there's some comets. Some comets come from outside the solar system, some of them come from the Oort cloud, which is beyond the Kuiper belt. This galaxy is Andromeda, and it's a spiral galaxy, and it's very similar to the Milky Way. And then the universe is everything. So galaxies and galaxy clusters and superclusters and just everything that we know is the universe. Stellar evolution of low mass stars. So we're going to do low mass stars, and then we're going to do high mass stars after that. Again, like what we need to know, what might come up in a 6-mark question that you can write down and get loads of marks. We'll do pretty pictures on the next slide. Okay, what is a nebula? It's a very, very big cloud of gas and dust. The gas is mostly hydrogen, and in this gas, pockets may form, perhaps caused by a shock wave, perhaps by a supernova, and then these pockets of gas are pulled together by gravity, and the temperature gets bigger and bigger and bigger, and the pressure gets bigger and bigger and bigger, and then your protostar becomes a proper star when nuclear fusion starts. So it switches on, nuclear fusion starts, and it becomes a main sequence star. So nuclear fusion happens in the core of our sun. Hydrogen fuses to helium, and our sun is balanced. You've got this nuclear bomb exploding outwards, causing radiation pressure, and then you've got gravity pulling inwards, and the two forces are balanced. Our sun is about 5 billion years old, and it's got about another 5 billion years to go. It's in the middle of its lifetime. At some point, the hydrogen in the core will start to run out, and then the fusion will spread outwards. And when this happens, our sun will expand. It will blow up like a balloon, and it will become much, 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 much bigger. The Earth will be swallowed up. It'll be that big. It will become much, much bigger and cooler. But then after that, gravity will pull it back in. The outer layers will be left behind. So you'll get these clouds of dust and gas. And that's called a planetary nebula. But the core will be kind of left exposed in the middle. So the exposed core, which pulls itself in, will be very, very hot and very, very dense, and that is a white dwarf. So we get a white dwarf surrounded by a planetary nebula. There's absolutely no reason why it should be a planetary nebula. It's nothing to do with planets, by the way. So the outer layers form a sphere of dust and gas. And then eventually the white dwarf will cool down and you'll end up with a black dwarf, okay, after a very, very long time. Yes, and fusion will stop. So here are some pretty pictures. The Orion Nebula, because it's in the constellation of Orion, the part of the sky that we call Orion. And within there's lots of stars being born. In this bit here, it's like a nursery for stars. The next diagram, radiation pressure and gravity are balanced. This is our sun at the moment, a main sequence star. And then, as I said, this will, when the hydrogen starts to run out in the core, because that's where fusion is happening, it blows up like a balloon and it becomes a red giant. But then it collapses and the outer layers are blown away, bottom left here, and we get this planetary nebula, it's called, and then the core becomes very, very small and very, very hot, and that's a white dwarf, and then eventually that cools down to a black dwarf. And this is for stars like our sun. A little bit about white dwarfs. Now, the white dwarf doesn't have enough gravity to squash atoms together, because atoms, as you probably know, are kind of electrons in orbit around nuclei, and the electrons don't like each other. So yes, and because they don't like each other, there's this thing that we call electron degeneracy pressure. And so that's the electrons like repelling each other so that you can't squash them anymore. If the gravity was stronger, then that would be able to happen. But in a white dwarf, there's not enough gravity. The maximum mass of a stable white dwarf, it's about 1.4 times the mass of the sun. And that's called the Chandrasekhar limit, named after this astronomer called Chandrasekhar. Yes, so that's the maximum mass of a white dwarf. Okay, large mass stars. So again, nebula, then a blue giant. Yes, this is a very large star. I think the biggest one they found is 315 solar masses, a very hot star. Because it's very, very hot, the rate of fusion is much, much bigger, so they don't last very long comparatively. As in our sun may last for 10 billion years, these guys only last for maybe 100 million years. So they have a much shorter life than our sun. When they expand, they become supergiants, which is very, very, very large red giants. Then when they collapse, the collapse is very, very quick, and it collapses incredibly quickly, and if you like, then it rebounds. There's an explosion due to this shock wave. There's a massive amount of fusion, and this big explosion is called a supernova. And then the outer layers are blasted outwards. And then what are you left with after that depends on the mass. If the star has a mass of between 10 and 25 solar masses, then we're talking neutron star. If its mass was at least 20 solar masses, see that there's a little bit of overlap. So it may become a black hole, it may not. But if it's at least 20 solar masses, then you get a black hole. So, pretty pictures. Orion, get outside in the winter and find the Orion, this asterism in Orion. You'll see there's Betelgeuse or Betelgeuse, which is a red giant, which apparently went supernova some time ago, obviously, but we may observe it in the very near future. There's the Orion Nebula is in there, in the sword, in the middle of the sword, and there's a Rigel there, which is a blue giant. You may have heard of Orion's belt there, and if you follow that down, that points down there somewhere is Sirius, which is the brightest star in the northern sky. I like Orion, lots of stuff in Orion. Is an animation of a supernova, and it's boom, there you go. And then what you're left with is a nebula. It's called a supernova remnant, and this is the Crab Nebula, and we observed this about 1,000 years ago. Chinese astronomers, amongst others, observed the explosion, the supernova that produced the Crab Nebula, and somewhere in the middle of there is a black hole. Neutron stars, a little bit about neutron stars. So atoms are forced together by gravity. We've overcome the electron degeneracy pressure, but now there's not enough mass to squash the neutrons together. So you've got your neutron degeneracy pressure. But anyway, the atoms are forced together by gravity to basically form a big ball of neutrons, a ball of nuclear material, which is nearly all neutrons. They are very, very, very dense. We're talking like if our sun was 10 to 15 kilometers in diameter, that's the density of a neutron star. So they're much, 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 much smaller. They are very hot when they form. They rotate, spin around very, very fast. And if you like, imagine our sun is spinning at the moment, and if it shrank, it would spin faster and faster, and that's like conservation of angular momentum, like an ice skater putting their arms in to spin faster. You know, as they get smaller, as their moment of inertia gets smaller, then their angular velocity gets bigger. Some of them more than 700 times a second, spinning around very fast. They have very strong magnetic fields as well. So learn some facts about neutron stars. Black holes. So now we've overcome everything. We've overcome electron, we've overcome neutron degeneracy pressure, and everything has collapsed. And theoretically, it's a point singularity. It's got infinite density. It is a point of infinite density. So the actual black hole is a tiny, 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 in fact, infinitesimally small point in the middle, okay, theoretically. At a distance now called the Schwarzschild radius, then not even light can escape. Okay, so on this diagram, the Schwarzschild radius, that's not the black hole, that's the sphere, which at that distance, even light can't escape. You may remember in the last video, I worked out an equation for escape velocity, yeah? V escape velocity is root 2 gm over r. If you put the escape velocity as the speed of light, that will tell you the Schwarzschild radius. There are lots and lots of black holes around in the universe. In our galaxy, there's lots and lots of black holes. And in the center of our galaxy, and other galaxies is a supermassive black hole. Yeah, 4 million times heavier than our sun. This animation is looking at the center of the Milky Way. This animation, the data actually took 20 years to get this data, but you'll notice that these stars are orbiting something, yes, something which we can't see, and that's the supermassive black hole at the center of the Milky Way. This is a Hertzsprung-Russell diagram. Well, what's that then? Well, look at the axes. We've got temperature and we've got luminosity, which, if you like, is brightness, the amount of light it's giving off. It's actually measured in watts, okay? It's the amount of energy per second that the star is emitting. Temperature at the bottom, it's a little bit weird because it goes from hotter to colder, so the axes are reversed. But what we do is, for all of the stars that we know, we plot them on this graph, and we see that stars fall into different regions on the graph. It's a very important graph for astronomers for understanding the different types of star and actually the evolution of stars as well. These 4 sections on the graph you need to know. Down here, bottom left, you've got hot but not very bright, so that's white dwarfs. They don't give off a lot of light radiation because they're not very big, but they are small, they are very, very hot. That's white dwarfs. We have giants, which are cooler. They do give off a lot of radiation because they are big. Up the top, red supergiants there at the top, very, very large giants. Our sun is in this big sausage in the middle, this yellow thing in there, that represents where our sun is, and that's called the main sequence. It isn't a sequence, yes, it's just the bit in the middle where the sun, the star is in the middle of its lifetime. It's where the star is stable. It's called the main sequence. Yes, when all observed stars are plotted on these axes, we see that they fall into these 4 groups. You might be asked to label this diagram, identify the different bits on this diagram. So giants are not very hot, but they're very big, so their luminosity is quite big. White dwarfs are very hot, but because they're very small, they don't emit as much radiation. And then stars like our sun in the middle stage of their lives are on the main sequence.